Today's lesson in AP Calculus basically pulls together everything you've ever learned about a curve. Max and mins, increasing, decreasing, concavity, points of inflection, asymptotes. And so we're going to put all of that together to create curves using all of the information that we can gather about a function. And so I have a list pulled up of things that we're going to want to consider as we create these graphs. As always, we always want to think about the domain and the range of our function. Domain, remember your x values, range or your y values. I don't, put a lot of time into domain range, but I go ahead and quickly look at, where are their x values where nothing will exist because it will make a 0 in the denominator. So I know there's going to be vertical asymptotes or holes, things like that. Logarithms, I have a logarithm in there. Oh, well, can't take a logarithm of a negative number. So I know my domain's going to be all positive numbers, things like that. Then you want to think about your x-intercept, where your x-intercept is going to be where f of x equals 0, so you want to find where your y equals 0. You want to find your y-intercept, you're going to find where your x equals 0. Symmetry is just nice sometimes to speed up the process of making the graph. If you know it's symmetric over the y-axis, then once you make the left side, you can quickly make the right side. Points of discontinuity, those would be holes or jumps. Holes in your graph would be what makes the denominator equal 0, and you can remove it. So if you can factor it out, what makes the denominator equal 0, you've got a hole in your graph. Vertical asymptote would be a non-removable discontinuity. Your denominator equals 0, but you can't remove it. Horizontal asymptotes, you're going to find by finding the limits as x approaches positive and negative infinity. Always both directions. Critical numbers. Then we're going to look for critical numbers. That's going to be where the first derivative equals 0 or is undefined. And once we have our critical numbers, we can then do the first derivative sign test to figure out where it's increasing and decreasing so we can find our relative maxes and relative mins. And then finally, we're going to look for potential points of inflection by finding where the second derivative equals 0 or undefined and checking concavity switches. If the concavity switches, you have a point of inflection. If the concavity does not switch, then you do not have a point of inflection. And you'll do your second derivative sign test to figure out that concavity. So we're going to do several examples where we're going to just go through this list, compile our information, and make our graphs. And we have a couple examples on here. I hope you have a sheet of notebook paper because I'm going to add, sorry, I'm grabbing some markers that write brighter. I'm going to add an example in here so you will need a sheet of notebook paper because there's no space on the notes. So first graph, we're going to work through this graph. If we look at domain, I quickly look at this and I notice, oh, well, there's nothing that makes the denominator equal 0, so x can be all real numbers. So my x is not restricted in any way. So I'm going to get my x-intercept. How do I get my x-intercept? Make my y equal 0, so I'm going to set 0 equal to x over x squared plus 1. Multiply by the denominator is going to disappear every time, so x equals 0. So my x-intercept is at 0, 0. How do I get my y-intercept? I make x equals 0, so y equals 0 over 0 plus 1. So I'm going to go ahead and start building my graph. So over here, I have an x and a y-intercept at the origin. So I'm going to go ahead and put that dot on my graph. Next in my list, I'm going to talk about points of discontinuity or vertical asymptotes. Is there anything that makes that denominator equal 0? No. X squared plus 1, there's nothing I can plug in for x to make the denominator equal 0. So there are no holes, there are no vertical asymptotes on this graph. Horizontal asymptotes. How do we find horizontal asymptotes? We find the limit as x approaches positive infinity. We find the limit as x approaches negative infinity. Can I use my shortcut rules on this equation? Yes, I can. The degree in the denominator is bigger. So what will the limit be as x approaches positive or negative infinity if the degree is bigger in the denominator? It will always approach 0. So my y asymptote is y equals 0. So I know I've got, I think I said y asymptote, I meant horizontal asymptote, is y equals 0. So let's continue on, and we need to find our critical numbers, which means we need to get the first derivative. And what rule am I going to have to use? Quotient. So denominator times derivative of the numerator minus numerator times derivative of the denominator, all over the denominator squared. So we're going to simplify this. So x squared plus 1 minus 2x squared. So we get 1 minus x squared over x squared plus 1 squared. So where do critical numbers occur? Where the numerator equals 0 or the denominator equals 0, because that would make it undefined. Will this denominator ever equal 0? No. What's x squared plus 1 going to be no matter what we plug in for x? It will be a positive number. This will always be positive, therefore I can't make it 0, but I can find where this equals 0. How does it factor? 1 minus x, 1 plus x, so x equals plus or minus 1. So now we're ready to do our first derivative sign test. What's an easy number to plug in? 0. We plug 0 into the first derivative. I'm going to plug it into this simplified first derivative. If I plug 0 in, I get 1 minus 0 is positive. What's this going to be no matter what? Positive. A positive divided by positive is positive. Are they double roots? They are not, so I'm going to switch, and they'll be negative and negative. So I know that this function is going to decrease, increase, decrease. F is going to do that. So do I have any max or mins? I have a relative min at -1. I have a relative max at +1. How do I get the y coordinate that goes along with the x coordinate? I plug these back into the original. So if I plug +1 in, I get 1 over 2, so 1/2. If I plug -1 in, I get -1 over 2, so -1/2. So right now I know I have a relative max at +1, 1/2. And I have a relative min at -1, -1/2. This is what I know so far. And I know that it decreases until -1, increases until +1, decreases again. So what's the last thing I need to figure out? I need to figure out concavity. So I need my second derivative. I'm going to put a little box here to separate this information. Okay, there was my first derivative. What rule am I going to have to use to get this second derivative? Quotient rule. But I'm going to save us time and go ahead and tell you what the second derivative comes out to be. And the second derivative comes out to be, well actually, we should practice this because it's an important technique for factoring. So let's practice the second derivative. So it's the denominator times, what's the derivative of the numerator? -2x, minus the numerator times, what's the derivative of the denominator? 2 times x squared plus 1 times 2x. What rule did we just do there? The chain rule. X squared plus 1 to the 4th. So I strongly recommend you pull out any GCFs to simplify this. What's a GCF here and here? We can pull out an x squared plus 1. What else is common? We can pull out a 2. We can pull out an x, and I'm going to go ahead and pull out the -2x. If I pull out a -2x and an x squared plus 1, what's it leave in the first spot? X squared plus 1. If I pull out a -2x, this 2x comes out and the negative, so it's going to make plus. This x squared plus 1 pulls out, so I'm left with 2 times 1 minus x squared. Can I distribute that 2? and get 2 minus 2x squared over the denominator to the 4th power. What's going to happen with x squared plus 1 and x squared plus 1? They cancel. And that leaves a cube. So we end up with negative 2x times x squared minus 2x squared, and 1 plus 2 makes 3 minus x squared over the denominator cube. Okay, so now we've got to find our second derivative where it equals 0 or is undefined. Will the bottom ever equal 0? No, this will never equal 0, but the top will. So negative 2x times 3 minus x squared is going to equal 0. Negative 2x equals 0. 3 minus x squared equals 0. So x comes out to be 0 and x comes out to be plus or minus root 3. So now we need to do our second derivative sign test because that's going to tell us concavity. Get in the habit of labeling which sign test it is. It's the second derivative. Let's put our zeros on here. What's an easy number to test? Positive 1. Positive 1 is between 0 and root 3. So we're going to try 1 out, and we're going to plug it into the second derivative right here. Negative 2 times 1 is a negative. 3 minus 1 is a positive. And what's the bottom going to be no matter what? Positive. What's a negative times a positive divided by a positive make? Makes a negative. 1 is a negative. Are any of them double roots? None of them are double roots, so it's going to alternate. So this means that f is concave down, concave up, concave down, concave up. So I have points of inflection. Where are my points of inflection? At negative root 3, at 0, and at root 3 because the concavity switches. How do I get the y coordinates that go with those x coordinates? I plug them back into the original. So if I plug 0 into the original, I get 0. If I plug root 3 into the original, I probably am going to want to use my calculator. I'm going to get root 3 divided by 4, whatever that decimal is. And I'm going to get negative root 3 divided by 4 when I plug in the other. I don't know what that decimal is, but it's a very small decimal. So I've got a point of inflection over here at negative root 3, which is like negative 1.7 and then a really small decimal. And positive 1.7 and a really small decimal. And I've got a point of inflection at 0, 0. So now it's time to draw my curve. So I'm supposed to be decreasing, concave down. So decreasing, concave down until negative root 3. I continue to decrease, but then I'm concave up. Then I'm still concave up, but I'm increasing. I'm getting that from this. I'm increasing starting at negative 1. I continue to increase, but now I switch to concave down. And then at positive 1, I start decreasing, but I'm still concave down. And then at root 3, I'm still decreasing, but I switch to concave up. And so I end up with my final graph. So basically, we're pulling everything together that we learned to do with derivatives to create these graphs. So let's look at example 2 in your notes. And unfortunately, I can't pull example 2 up higher on my screen. As high as it goes. So I'm going to do all the work above it and keep it down here at the bottom. We are working with example 2. Hopefully you might need notebook paper yourself. You might want graph paper for your homework tonight. So domain, I look at this and I quickly ask myself, is there anything that's going to make the denominator ever equal 0? No, there is not. So I'm going to skip on to my x and my y intercepts. So actually, I'm going to, just because I think it'll be more helpful when I do my horizontal asymptotes, I'm going to change this just a little bit. So in your notes, change this x to a 4x, and change this 2 to a plus 15, okay? Really doesn't change much other than my horizontal asymptote. So still the domain is all of our numbers. There's nothing that makes the denominator equal 0. So we're going to start with x-intercept. How do I get my x-intercept? Make my y 0. So 0 equals 4x over the square root of x squared plus 15. When I multiply both sides by the square root, it disappears. So x comes out to be 0. So my x-intercept is 0, 0. Y-intercept, how do I get y-intercept? Make my x 0. So y equals 0 over root 15, which is 0. So my y-intercept is also 0, 0. That tends to happen a lot, but not always. So I have an x and a y-intercept at the origin. So let's continue on. I'm going to give myself some more space and talk about the vertical asymptotes. Is there any way that x squared plus 15 will equal 0? No, there is not. So there are no holes. There are no vertical asymptotes. So let's skip to horizontal asymptotes. How do you find horizontal asymptotes? You get your limits as x approaches positive infinity and as x approaches negative infinity. So we have 4x over the square root of x squared plus 15. We have 4x over the square root of x squared plus 15. What is that top limit going to be? Who remembers? It is going to be 4. These are the same degree because what's the square root of x squared? The square root of x squared is x. So x and x are my highest degree, so it is the ratio, and so it is 4. However, when I go to negative infinity, the bottom is going to be a positive number. What's the top going to be? Because the square root, because when I square it, it's going to become positive. But what's the top going to be? It's approaching a large negative number. So you've got to think of this as being a negative divided by a positive. So it is still going to be the ratio 4 to 1, but not positive 4 to 1, but negative 4 to 1. So I have two horizontal asymptotes. As x goes to positive infinity, this graph approaches positive 4. As x goes to negative infinity, this graph approaches negative 4. This takes us back to chapter 3 when we learned about horizontal asymptotes. If you don't remember doing problems like this, you might want to go back and refresh your memory before this test. So let's move on to first derivative because we need to be able to find max and mins. So we're going to have to get the derivative, and I see here we're going to have the quotient rule with the chain rule inside. I'm going to save us a little bit of time here and go ahead and tell you that it comes out to be, if I can find it, I thought I had it worked out. Can't read my writing. Okay, so maybe I don't have it worked out. I thought I had already worked this out. So let me check my work. Oh yeah, so it is, I just can't read my writing. It comes out to be 120 over 2 times x squared plus 15 to the 3 halves. Okay, so that's what the first derivative comes out to be once you do the quotient rule. I'm just saving us time. So we've got to find where the first derivative equals 0 or is undefined. Will anything ever make the numerator equal 0? No. Will anything ever make the x squared plus 15 equal 0? No. So there are no critical points. However, this is very important. We can still tell something about the slope. There are no critical points, which means this is going to be a strictly monotonic curve. It's either going to be increasing the whole time or decreasing the whole time. We just have to pick any x value we want and figure out what the slope will be. Pick an x. X is 1. If I put 1 in, I get a positive divided by positive. Pick a negative number, negative 8. Negative 8 become positive, positive over positive. Put 0 in. Positive over positive. No matter what number I plug in, the slope is always positive. So this curve will always increase. So f is increasing the whole time. So let's continue on. We need our second derivative. So I'm going to rewrite this. 120 divided by 2 is 60. X squared plus 15. I want to avoid the quotient rule, so I'm going to write it as negative 3/2, so I don't have to use the quotient rule. So now let's get the second derivative. So the second derivative is, bring the negative 3/2 down, that makes negative 90. X squared plus 15 to the negative 5/2 times chain rule 2x. So let's clean this up a little. So the second derivative comes out to be negative 180x over x squared plus 15 to the 5/2. So what's going to make my numerator equal 0 if x is 0? What's going to make my denominator undefined? Will the denominator ever equal 0? No, it will not. There's nothing I can plug in to make a positive number plus a positive number become 0. So we're going to do our second derivative sign test. And pick an easy number, positive 1. Plug 1 in. We get a negative over a positive is a negative. It's not a double root, so it does alternate. So this is going to go from concave up, or y is going to go from concave up to concave down. And then what's my point of inflection? Well, x is 0. How do I get the y coordinate? Plug it in the original. Here's my original, and I get 0, 0. So I have a point of inflection. I have no max and mins because there were no critical numbers. I know this function has to fit between the two horizontal asymptotes, and I know that it's going to increase the whole time. It's going to be concave up and then concave down. So this curve is going to curve up, and then it's going to curve down and approach the horizontal asymptotes and have increasing slope the whole time. It's very important that you are not on this homework deciding, oh, I'm just going to put this original function in my calculator and copy the picture. For one thing, you're not practicing any calculus. For another thing, the test is no calculator. So if you don't practice making these graphs by yourself without copying a picture from your calculator, you're going to lose a whole lot of points on my test. You have a pledged assignment on this on Tuesday night. There are 2 graphs on there. If you miraculously have the correct graph and your work does not support that, you will get no credit from me. Plus, we will have an honor offense because you're going to be told that you're not allowed to graph those on your calculator. So on your homework tonight, do not graph them on your calculator. You will get more credit from me on the test and on the pledge assignment if your work has a small mistake, but your graph matches the work that you create. You will get more points. Because if you make one, let's say you made one little error here and you had negative then positive, and so your graph happened to have the concavity flip-flop, you might lose one little point because you made the mistake here. I'm not going to count it wrong here as long as this matches your work here. So make sure you are doing all this work on your homework and you are creating the graph, not your calculator, okay? Not a programmed calculator. So we're going to add an example that is not on your notes because it's a good one that I didn't put in the notes. So let's look and see. We'll call this, I don't know, example 2b if you want to. So the example we're going to do is y equals 2x squared over x squared minus 1. So we're going to go through our list. So the first thing, I'm just checking the time on the video. The first thing we want to do is, domain. I can already tell, oh, we don't want x to be 1 or negative 1, so there's going to be some asymptotes coming up. But first, let's do x-intercept. If I make y 0, I end up finding out the x-intercept is 0, 0. Y-intercept, I make x 0, I find out the same thing. So when I make my graph, I'm going to go ahead and put my 0, 0 point on here. We said the domain couldn't be 1 or negative 1. Are those going to be vertical asymptotes or holes? Those are going to be vertical asymptotes. I can't remove them. So I have vertical asymptotes at 1 and negative 1. So I'm going to go ahead and put those on my graph. Horizontal asymptotes. I find as the limit approaches positive and negative infinity, the degrees are the same, so the ratio is going to be 2. The only time negative infinity will give me a different asymptote is if I'm dealing with square roots or if I'm dealing with logarithms or something like that. But if it's a straightforward rational function with no square roots, it'll be 2, whichever direction I go. So the a horizontal asymptote at 2 in both directions. Okay, so we need our first derivative. And we're going to have to do the quotient rule because I'm trying to speed up the process of this. I'm going to go in and tell you because the book actually found this first derivative for me. Negative 4x over x squared minus 1 squared. That's what you get once you do your quotient rule. So we need to find where the numerator equals 0. Where will the numerator equal 0? At x equals 0. So I'm going to put that on my sign test. Where will the denominator equal 0? This is the same as x plus 1, x minus 1 squared. At 1 and negative 1. And what do we notice about those? This is squaring this, so it's squaring these, which means these factors happen how many times? Twice. So these are double roots. That's going to affect my sign test. So let's pick an easy number to test. 2. We get negative 8 over, what's this going to be once I square it? No matter what this is, when I square it, it becomes positive. So negative 8 over a positive number will be negative. It's a double root, so this will be negative. That's not a double root, so it switches. This is a double root, so it's positive again. So this function is going to increase, increase, then decrease, decrease. What's happening at 1 and negative 1? Those are vertical asymptotes. They don't exist. Good. So this is my only maximum. And we know that's at 0, 0. So now we need to get the second derivative. And again, to save time, I'll tell you, because the book did this one too, that is 12x squared plus 4 over x squared minus 1, and I think it's cubed. Okay. So first we have to figure out what's going to make that numerator equal 0. Well, if this is a positive number times a positive number, and I add a positive number, is that ever going to equal 0? No, it is not. The bottom is going to equal 0 at 1 and negative 1. Is it a double root still? No, it's a triple root, which means the signs will change. So let's plug in an easy number. 0 is easy. Plug 0 in, we get a 4 over a 0 minus 1 is negative 1. Negative 1 cubed is negative. So positive 4 over a negative 1 makes a negative. They're not double roots anymore, so they are going to switch. So I'm going to be concave up, concave down, concave up. Are these points of inflection? The concavity switched, but the points don't exist. If I plug negative 1 in, I get undefined. If I plug 1 in, I get undefined because what's happening at 1 and negative 1? Vertical asymptotes. So I need to draw a curve that's increasing until 0, concave up until negative 1, and fits between my asymptotes. So this is increasing, curving up, and fits between my asymptotes. Then it still needs to increase, but be concave down until 0, with a maximum at 0. Then it's supposed to decrease and still be concave down. And then finally it's decreasing, concave up. Where can I fit decreasing concave up on this side and be between the two? The only way to fit it is up here in the top corner. Good. So for your homework, you're supposed to do example 3 and 4 in these notes. So I'm going to skip 3 and 4, and then we're omitting example 5 and going straight to example 6. So 3 and 4, you're doing part of your homework, and we're going straight to example 6. So last example on your notes, 3 and 4 are part of your homework. So when we check tomorrow in class, that'll be part of our check along with the homework problems. So let's see, example 6. Oh, and I do need to tell you something about the homework. I'll tell you right now, because I might forget it then. On number 23, on your homework assignment, when I carried over my Word document to my Google document, for some reason it didn't carry over the equation. I went ahead and made the first derivative for you because it's a very long quotient rule. So I did it for you to save you some work and some time on your homework tonight. So when you look on your homework, page 323, number 23, I've already done the first derivative for you to save you time. So write this down somewhere on your homework syllabi or something so that you don't have to find that. It takes a while. It's quite a convoluted quotient rule. So you have 7 problems in your book, and then you have 2 from your notes to do on section 5. So let's go back to example 6. So example 6, we've got y equals 8x squared minus x to the 4th. In terms of domain, what can x be? All real numbers. X can be anything. If I want to get my x-intercept, what do? Make y 0. So I'm going to pull out a GCF. And x comes out to be 0. And x comes out to be the square root of 8, which is plus or minus 2 root 2. So we're going to go ahead and put those over here. So 0, 0, and then 2 root 2 is about 2.8. So I've got x-intercepts at 2.8 and negative 2.8 and 0. How do I get the y-intercept? I make x 0. If I do that, I get 0, 0. Now I need vertical asymptotes. Is there anything that makes this undefined? No, so there are none and there's no holes. How do I get horizontal asymptotes? I find the limit as x approaches positive or negative infinity. Or if I plug in bigger and bigger numbers, what is that function going to do? It's just going to get bigger and bigger and bigger. So there is no limit, which means there are no horizontal asymptotes. So let's move on to the first derivative. The first derivative is 16x minus 4x cubed. Find my critical numbers, pull out a 4x. We get 4 minus x squared. So my critical numbers are 0, positive 2, and negative 2. So now you need to do your first derivative sign test. Pick an easy number, 1. Put 1 into your first derivative, you get 4 times 3 is a positive. Are any of them double roots? No, so it's going to alternate. So this function is going to increase. F is going to increase, decrease, increase, decrease. So where do I have relative maximums? At negative 2 and at positive 2. How do I get the y coordinate? Plug them into the original. So I'm going to go ahead and tell you, if you plug them into the original, you get 16 and you get 16. So my maximum points are at negative 2, 16 and positive 2, 16. My relative minimum, I plug in 0, I get 0. So I have a maximum point at 2, 16. I have another maximum point at negative 2, 16, and then I have a low relative minimum point at 0, 0. Didn't even make them even, did I? Okay. So now, last thing we need is concavity. So we need the second derivative. Or if this is my first derivative, then my second derivative will be 16 minus 12x squared. Set that equal to 0. So 16 equals 12x squared. X squared equals 16 over 12, which is 4/3. Square root both sides, you get the positive or negative 2 over root 3. And that decimal, I didn't figure out. 2 over root 3. You'll have to get that on your calculator. So we're going to do our sign test for concavity. So this is the second derivative sign test. So pick an easy number. Easy number to pick is 0 in the middle. Put 0 in my second derivative. What do I get? I get 16, which is positive. These are not double roots, so they alternate. So my original will be concave down, up, down. So I have points of inflection at negative 2 root 3, comma something, 2 root 3, comma something. How do I get the y coordinate that goes with those x coordinates? I plug the x's in the original. And I did not write those down, so I'm not sure what the decimal comes out to be. So real quick, let me go grab my calculator because I left that back here on my desk. So 2 divided by root 3 is something. 2 divided by, 2 divided by second square root 3 is, so these are 1.154 and negative, or 1.155 and negative 1.155. Okay, so if we plug that in, we get, I'm gonna square it, times 8 minus okay, so it comes out to be 8.8 repeating. They both come out to be the same. So somewhere around 8 at negative 1.15, my concavity is, and positive 1.15, my concavity is switching. 8.8, 8.9. Okay, so let's draw this graph. We're increasing until negative 2, where when we get to a max, then we decrease. We should be concave down until negative 1.15 and then concave up. So we go through our x-intercept. So we're concave down and increasing. We're still concave down right here. We switch to concave up, still decreasing. There's my minimum. Then I'm increasing, but still concave up. Then I switch to concave down, and then I'm concave down and decreasing. I go through my other x-intercept. What basic shape graph did I end up with? An upside down W. What does a negative x to the 4th equation make? An upside down W. So go ahead and get started on these graphs. You do have 9 in your book. Not all of them are graphs, and then you have the 2 in the handout. And then you also have hopefully already done your L'Hopital homework, which I suggested you do in the early part of the day.